And okay, so Barbara, you can start when you want. Thank you very much.
Okay, thank you very much, Isabel, and the organizers. It's a wonderful presentation, and I think that it's me, the one that is lucky to have been in Granada many times because it's a wonderful place. Okay, Sevilla as well is a wonderful place. I was just once, but it's beautiful. So let me just use this pointer. Okay. So as Isabel, it's really a pleasure to talk to all these friends that I see that I don't see, but I know are in the audience by their names. And I really hope to be there, not virtually, as soon as possible for all of us. I mean, anyway, let me start. So as Isabel told, I will talk about hypersurfaces with constant higher order mean curvature. Let me first of all describe the object just to set up the frame where we are working in. So we will consider an immersions of a manifold of codimension 1 in another Riemannian manifold. And we will consider the R-mean curvature of the immersion, where the R-mean curvature is defined as the elementary symmetric function of order R of the principal curvature. So a very simple object. Of course, when R is equal to 1, it is the mean curvature. When R is equal to 2, 1 has the scalar curvature. And when R is equal to n, 1 has the Gauss-Kronecker curvature. So, and all the ones in the middle. In fact, the HRs carry a lot of geometry. It's not very mysterious, the reason. I mean, they are the symmetric function of the principal curvature, so they carry a lot of geometry. And they come from far away. Let me just describe when they were introduced, at least to my knowledge, to be studied. I mean, of course, the symmetric function of something is something very usual, but they were studied from the geometrical point of view by Robert Riley in 1973, because he studied the following set of variational problems. Okay, like that. He considered an immersion in Rn plus 1. I will take M compact, but in fact, one can also consider a non-compact surface, submanifold, hypersurface, in fact. A variation of the immersion is a differentiable map from 0, 1 times m, and such that at any stage it is an immersion. So for any fixed t, it's an immersion. The first one is x0 is exactly our immersion. And then you can consider, when t varying, you can consider v of t, that is the volume. This is in fact if you have a compact manifold without boundary, this is the difference between the volume at stage 0 and at stage t. Okay, the difference with sign. And then you can consider the weighted area, that is this AR, the integral of the HR function, that is the symmetric function, the R-symmetric function of the principal curvature. And then you can compute you can differentiate this with respect to t and compute it in 0, and you have this very simple formula. Of course, when R is equal to 0, this is the area. And then you can denote by JR of t AR, so the R area, plus lambda V of t, where lambda is a constant. And then it's very easy to see that J prime of R is this integral, so this number times this scalar product. And of course, if M is constant curvature HR plus 1, then one can choose lambda equal to n the binomial of n r plus 1, hr plus 1, and m is a critical point of JR. When r is equal to 1, it's a very well-known functional, but you can define it, rightly define it for any function, curvature function. And this characterization is also possible in any space forms. So hypersurfaces with constant r symmetric function of the principal curvature are critical point of a functional in space forms. I specify space forms because in general this is not so, this doesn't work, because you have here the curvature of the space entering into the integral, so it's not a critical point of this kind of functional if you are not in a space form. And we will go back to this in the end if we will have some time. Okay, so now I hope you are convinced, if you were not before, that HR hypersurfaces are interesting. And I will describe some more properties that they have that makes them more interesting. One of the properties that we have to deal with is ellipticity. And in fact, what I mean is that in general, if you put HR equal to a constant, you get a second order fully nonlinear partial differential equation. I am not very precise here, but you can think, for example, of writing your hypersurface as a graph over the tangent space. Then you have a function, and the function satisfies a second order fully nonlinear partial differential equation. And if r is equal to 1, is the mean curvature equation, and it's not fully nonlinear, it's just a quasi-linear equation. Such equation, in general, when HR is positive, is elliptic, but not always. It's elliptic provided that the vectors of the principal curvature belongs to the positive cone, this gamma r, that is the component of HR positive in Rn that contains the point 1, 1, 1, 1. Okay, so you need some assumption in order to be elliptic. And in general, HR is equal to 0, that is, that would be R minimal hypersurfaces, does not yield an elliptic equation. Of course, when R is equal to 1, yes, because you have quasi-linearity. But in general, this doesn't work. Sometimes, yes, but not in general. Ellipticity is important. Everyone knows, I think, in the audience, that it's important because it yields the maximum principle. And the maximum principle is a wonderful tool to compare hypersurfaces. And everyone knows the picture is explain everything alone, that if you have two hypersurfaces that satisfies the same elliptic equation, and they are tangent at a point, and they are one on the one side of the other, then they coincide. So this is the maximum principle, geometrically speaking. But let me explain when and which is the maximum principle in this case. Because as I told you, you need to be in the positive cone and so on. So we denote by n the orientation on our hypersurface, and we take the principal curvature, the vector of the principal curvature, and then we have this maximum principle when HR is positive, and this is due to Fontenelle-Silva. So you take two hypersurfaces in a Riemannian manifold with the same HR positive. You take a point where the two hypersurfaces are tangent, have the same normal, and your vector of principal curvature belongs to this positive cone that I told you before. Then you have the maximum principle. If M remains on one side of the other one, of the other surface, of the other hypersurface M prime around P, then they must coincide. Okay, so this is the same provided that K, and K prime belong to the same leaf, as one say. Then, when you have HR equal to 0, the same maximum principle holds, and this is due to, again, to Honey-Leite and also Fontenelle-Silva. everything is Brazilian here in this page. You need, in order to have maximum principle, you need a further assumption, and that is that the rank of the Gauss map of one of the two hypersurfaces is greater or equal than R if HR is equal to 0. Okay, and then it works. This assumption that the rank of the Gauss map coincide is greater or equal than R means that there are at least Ki R of the Ki that are different from 0. And these two maximum principles, are the proof of them relies heavily on the properties of the hyperbolic polynomials that were studied by Garding a long time ago. So now we know that we have the maximum principle, so we can start to work. And let me tell you a couple of results that in the 80s and also later gave a new life, let's say a new life to the theory of hypersurfaces with a constant symmetry, HR equal to a constant. The first one is due to a series of papers by Caffarelli, Nirenberg, and Sprague that in the 80s studied the existence and uniqueness of solution for the Dirichlet problem for HR equal to a constant. In fact, they study a more general equation, but it includes, it's a very important, this HR equal to a constant is a very important example of those equations. And in order to study existence and uniqueness, they use the continuity method. So they need a priori estimate for a solution. And the important thing here is that being a fully nonlinear equation, they could not use Schauder theory, the theory that guarantees, Ladizanskaya, Uralcheva, and Schauder, that guarantees that if you have C1 estimates, then you have C1 alpha and then C2 alpha. That is what you need to prove the existence. Here, you have to prove directly C2 estimates in order to prove existence, let's say, to prove existence. And then for the continuity method, you also need the existence of a subsolution. But the very important thing in those series of papers was exactly their method to find the C2 estimates independently from Schauder theory and so on, a direct estimates. This was the first very strong result. And then there is the study of, this is later, in the 80s, but later, of the classification problem for compact hypersurfaces without boundary let's start with the Euclidean case. That is due to Ross and then to Korevar, because Ross started doing that for scalar curvature, and then Korevar have extended the result. And the result is that the round sphere is the only compact without boundary hypersurface with HR equal to a constant embedded in Rn+1. And this is clearly an extension of Alexandrov's theorem. I will not talk too much of the counterexample for immersed and so on. So the case R equal to 1 is Alexandrov theorem and is by the maximum principle, while the Ross method was quite different to prove. Ross method to prove this theorem was quite different from maximum principle. And then there are plenty of papers by Ross, Corban, Ross Montiel, and so on, that they extended the result in space forms with different techniques. Later, there are also some other results where instead of considering just compact hypersurfaces, one consider hypersurfaces with boundary. Boundary in a plane, boundary, it depends on your sphere. There are many results there. This is references are far to be exhaustive. It's just some of them. Okay, but I will not talk about that. Just a little bit of history. What we are going to do is dealing with the three kinds of problems if we have time. And the first one is three, but it is Bernstein, Shin, and Osserman type theorem. That is, study the geometry of a complete hypersurface with constant HR with respect to the geometry of the asymptotic boundary of this hypersurface. And our ambient manifold will be the hyperbolic space or the product of this H and cross R. That is a nice space because there are many symmetries, but the sectional curvature is not constant. So we have different phenomena appearing. So this will be the first group of results. Then I will talk just a little bit about the rigidity. The question is if it is possible to perturb the arming curvature of a Eurosphere or of an equidistant sphere in the hyperbolic space, keeping it positive everywhere and constant outside the compact set. So a perturbation problem. And the third one, if I really have time, I would like to spend a couple of words about stability. As I told you before, in general, stability is, while it is a well-defined, a well-established notion in space forms, it's not at all common or established in any Riemannian manifold for arming curvature surfaces. Okay, so let's start with HR equal to a constant, positive constant, on a non-compact manifold in the hyperbolic space. So let me tell you the first result, that is a Bernstein type theorem, and is in collaboration with Zhu. So let M be a complete hypersurface properly embedded in the hyperbolic space with constant HR, positive, and consider the asymptotic boundary of M. We are in the hyperbolic space, so everything is well defined. So we have the following. This can be, if the asymptotic boundary is a point, then M is Eurosphere, and I call it Bernstein type theorem. Or if the asymptotic boundary is a sphere and M separate poles of the sphere at infinity, I'm not entering details, but it's clear because it's, poles are poles, and the boundary must separate poles. Then M is either an equidistant sphere or a hyperplane. I will, this result, in fact, is a generalization of a result that holds for mean curvature and is due to the Carmolozon. And the title of the paper is exactly a Bernstein type theorem in the hyperbolic space. So this is why is a Bernstein, we call it Bernstein type theorem, but in fact it is. Bernstein is just that, in fact, Bernstein theorem is that a minimal graph, entire graph is the plane. Now here it's not a graph, it's a little bit different, but if you, for example, if you have just one point at infinity, in some sense you have a graph. So this is why it's a Bernstein type theorem. Okay, so let me prove, sketch the proof where of the case where the boundary at infinity is a point. All right, the first thing that we have to do is to prove that M has a strictly convex point. Why this? Because this will allow us to use the maximum principle. Okay, because if there is a strictly convex point, then you are in the case that you are in the positive cone with your curvature, and so it's fine. So let me prove it by picture. So we take the alpha space model for the hyperbolic space, and you take M, the hypersurface, and then you start to, you take a family of equidistant sphere, the blue one, with a curvature K0. As they are umbilic, curvature means any curvature, mean, HR, but also all the principal curvature. And this is what we are interested in, the principal curvature. So you start with one that does not touch M. This is possible because the boundary at infinity of M, we put it very far away. And then you continue increasing, you just blow up, but this is an isometry of this space. So you will touch for the first time the hypersurface. And at this point, you consider the vertical direction and also any tangent direction x. And you consider the two plane that is generated by the vertical and the x. And then you consider the intersection of the plane with M, so this curve gamma x, and it's obvious for the position in the space that the curvature of this gamma x is larger or equal than K0. And as you can do it for any tangent direction, you see that P, in fact, is a strictly convex point. So now we can use the maximum principle, and we will do Alexandrov reflection in order to prove that your hypersurface is a Eurosphere. Okay, so we take M again. This divided the space into two components, as I wrote here, omega plus, omega minus. This is always the boundary at infinity. There is a plus here that is a mistake, but anyway, I cannot erase it now. And then I want to do Alexandrov reflection with hyperbolic hyperplanes. So I start with a blue far away hyperplane, and then I go farther, I approach M, and I have a first contact point, the red one here, and then I continue a little bit. And I do Alexandrov. So here, for example, is Alexandrov reflection. The green part is the Alexandrov reflection to the yellow hyperplane of the red part below the yellow hyperplane. And I claim that, of course, at the beginning, the reflection that I call M star T is contained in omega plus, but I claim that this holds forever, for any T, okay? In fact, if one stops to hold, if these properties stop to hold, there will be a first tau where the two hypersurfaces, the reflected one and the original one, M, touch. And here you have a contradiction by the maximum principle. So this holds forever. And it's really just thinking a little bit about that if it holds forever, then the tangent plane to M is everywhere horizontal, and this means that M is Eurosphere. So the proof is really very, very simple. Okay, so the rigidity result that I promised, let me first state it, and then I will do some comments. If you take a hypersurface in the hyperbolic space, which coincide with the Eurosphere outside the compact set, and the arming curvature outside is 1, and in this compact set B is larger or equal than 1, or everywhere smaller or equal than 1, then sigma is Eurosphere. So you cannot perturb, in fact, provided that you assume something on the HR curvature. I will not explain anything about that, but I want to say that for this result, we were totally inspired by this paper by Rabat, Swam, because he did it for mean curvature. And in fact, the result is the same for HR curvature, provided that you can use the maximum principle, but you can, because here you have plenty of a strictly convex point. And of course, the same holds for equidistant spheres, but it's, I mean, you can replace or a sphere by the equidistant sphere. And the case of mean curvature in Rn, in fact, is due to Gromov. We learned it in a Rabat paper with completely different method, nothing to do with maximum principle. But this proof is very easy for us. I mean, for people that are accustomed to use maximum principle. Okay, so now I go out of the hyperbolic space and I start to talk a little bit of HR hypersurfaces in the product of the hyperbolic space with R. Okay, so what we are going to do is to revisit in this space and for HR hypersurfaces, two classical results that holds for minimal surfaces with finite number of ends, 2 ends. Or so just a quick picture. We will use in this case the disk model for HN for the hyperbolic space, and so our space is just a cylinder, appears like a cylinder with this metric that I wrote here. Now I will show you a couple of pictures from that I borrowed for a paper by Martin Mazzeo Rodriguez, that are these two pictures. The left one is what one called the vertical catenoid, and it's just H equals 0 in H2 cross R, invariant by rotation around the vertical axis. Okay, this is the vertical catenoid, and you see the two ends are asymptotic to a hyperbolic plane. And then there is something quite different that are horizontal catenoids. They were described in this paper by Martin Mazzeo Rodriguez, and they are, of course, is topologically a cylinder. There are two ends, and the two ends are asymptotic to totally geodesic plane, vertical, totally geodesic plane. You see this and that. So, of course, they are really different, and it's sorry, H equals 0, minimal surfaces. What you there is a big difference between these two cases, because, for example, if you look at total curvature, the left-hand side is not finite. Of course, it's asymptotic to H2, and this one on the right side is finite total curvature. So you need to deal with these two cases in a different way. Okay, so let me first treat the left side case for HR equal to 0 in HN cross R, and I call it a Shin type theorem. Everyone know, but I mean, I will tell you later. So you take a complete connected embedded hypersurface in HN cross R minimal, HR equals 0, and I take also this condition, HR plus 1 different from 0. This guarantee ellipticity. Then you assume that M has two ends, and each of them is a vertical graph whose asymptotic boundary is a copy of the boundary to infinity of the hyperbolic space, just like the catenoid before. Then M is isometric by an ambient isometry to a rotational invariant hypersurface. So it's an R catenoid, if you want. So this is clearly inspired by the well-known theorem for minimal surfaces by Shin, a complete connected minimal surface immersed in R3 with two embedded ends of finite total curvature is a catenoid. Of course, we cannot take finite total curvature here, doesn't make sense, but finite total curvature for Riction implied that the ends were regular. And so in some sense, in this case, we assume regular ends, okay, in order to get the same results. Of course, okay, the minimal case was already studied by myself, Arp, and Tubiana before. And here in this paper with Albert and Santos, we had also to classify the rotational, R minimal rotational invariant hypersurface here, yeah, because they were not before classified. Okay, now I will go now to look at the picture that was on the right side of the slide, the horizontal catenoids, the one that has a vertical asymptotic plane, ends asymptotic to vertical planes, but we will take HR equals 0. And our aim is to generalize, in fact, the following classical result. That is this theorem due to Huber and Osserman. Let M be a complete, oriented, immersed minimal surface in R3 with finite total curvature. Then M is conformally equivalent to a compact Riemann surface with a finite number of points removed, that are the ends of M. And the Gauss map extends meromorphically to the puncture. So a minimal surface with finite total curvature is very compact, okay, because you know really how it is, which is the conformal structure, and also how to extend the Gauss map. This theorem was extended by Anderson to higher dimension, but of course, if you change the dimension, you lose some of the properties of the minimal surfaces. So you are not going to look the conformal structure, but the diffeomorphic structure. So you have diffeomorphic here, and the Gauss map does not extend meromorphically because you don't know much about the Gauss map, but you know that Anderson proved that it extends to a smooth. It was smooth at the puncture. We study complete hypersurfaces in HN cross R. First, assuming that they satisfy a finite total curvature assumption. So we don't take minimality at the beginning. That was what Huber did, in fact. I mean, he did for minimal, for surfaces in R3. So we are going to study that kind of problem. And then we specialize assuming that M has a 0 R mean curvature. So we start first studying hypersurfaces with a, we will see strong finite total curvature. I will tell you in a while what is this. Our assumption on the curvature, on the total curvature, will be finite strong total curvature. Let's state the theorem, and then I will tell you what finite strong total curvature is. So we take an immersion of an orientable complete hypersurface with a finite strong total curvature. Then what we are able to prove is that the immersion is proper, and that the M is diffeomorphic to a compact manifold minus a finite number of points. So the result analogous to the result that we saw before. But we have this finite strong total curvature assumption. So let me define this norm. So we take the shape operator of M, and we define this norm that I will not pronounce. It's the norm of the second fundamental form in a suitable weighted Sobolev space, of course. And we say that if the norm in this space is finite, if the norm of the second fundamental form is finite, then the hypersurface has finite strong total curvature. You see that here, the key point is that you have an assumption on the derivative of the shape of the norm of the shape operator. not only on the integral of the norm. Okay, but this norm that looks ugly is not so ugly, because I mean, it's not a norm. We did not invented anything. It was used by Bartnik in a pioneer paper, and used it to define a suitable decay infinity of a metric of a manifold that guarantees that the ADM mass was a geometric invariant. I mean, does not depend on the coordinates. So it's to define asymptotically flat spaces. And it was already used by Carmo Albert for hypersurfaces in Rn+1. So we use it again, and it works here again as well. Okay, so we have the first part of Osserman theorem. The manifold is diffeomorphic to a compact manifold minus some points, and you can extend the Gauss map. No, sorry, I was telling you, you can extend the Gauss map. It's wrong. It's not true. I mean, the theorem here is that immersion is proper. This is easy, and then it's diffeomorphic to a compact manifold minus a finite number of points. Now, we assume that HR is 0, and we get something more. So let me state the theorem that is a little bit more involved. We are going to say something about the ends of the hypersurface. The ends are neighborhood of the point that are removed. We already know that the manifold is diffeomorphic to a compact one minus point. So we can take the ends that are a finite number of ends. So we take an end of this hypersurface, and we consider the normal vector to it, and we consider a hyperplane, a vertical hyperplane. Keep in mind the picture by Martin Mazzeo Rodriguez, and you choose an hyperplane such that the boundary, the compact boundary of E, is contained in one of the 12 spaces determined by P. I mean, that's not half on one side, half on the other side. It's contained on one side. I see that Antonio raised an hand. So maybe he has a question?
Antonio, do you have a question? You can.
No, I have nothing, please. Excuse me. I only don't know very much the computer machine.
Okay.
Right.
Anyway, hi, Antonio.
Right. I'm happy to hear you here.
Thank you very much. So what you choose such plane, and you assume that this yellow stuff, that is the boundary at infinity of the end, when you consider the part contained in the cylinder, is contained in the boundary at infinity of the plane. You don't know what happens above and below, but you know this. Then what we are able to prove is that E, in fact, is asymptotically close to P, to the plane. And also that for any sequence of points converging to the boundary at infinity, the sequence of the normal vector becomes horizontal. That is like, so the convergence is also with the normal, because the plane has horizontal vector in the end. Everywhere, in fact, the vertical plane has a normal horizontal vector. But this happens for the end as well. Okay? So I will not try to do a picture with this pen, because I'm not able. Anyway, I hope it's clear. You have to think about this picture by Martin Mazzeo Rodriguez, and this is the picture, in fact. But it's in higher dimension with HR equal to 0. And oops, sorry. So in fact, this result generalized a result for minimal surface in H2 cross R that was proved by Auswirth and Rosenberg, and then was make precise in some other feature by Auswirth, Saarp, and Tubiana, and myself. But in fact, the proof is completely different. It takes inspiration in this other paper by Saarp and Tubiana. And of course, it's completely different because when you work with n larger than 2, one loses completely the technical support of the complex analysis that was very heavy, counting very heavy in the proof for minimal surfaces in H2 cross R. And working with R larger than 1, you weaken also the technical support given by the quasi-linear PDE. So it seems reasonable also to us to require a stronger assumption of the total curvature. I mean, it seems reasonable. We don't know if you can avoid it. I mean, hopefully you can avoid it, but we're not able to do it. Okay, so now I have some time to talk a little bit about stability. I recall you that the immersion X with of course, I forgot to write, if you have that the R+1 mean curvature is constant, then it is R stable if it is a minimum for this, a local minimum for this functional J that was defined by Riley. Okay, so J prime of 0, J prime R0 is 0, and then J second is larger or equal to 0. This is the usual notion of stability for a submanifold. And this notion in Rn+1 can be extended to space forms. And this was studied by Barbosa-Colares in '97. But then if you go to a general Riemannian manifold, there is not known functional for which hypersurfaces with constant HR+1 are solution of the associated variational problem. There is something, for example, Elbert did it for scalar curvature in Einstein manifold. But in general, you don't know, because when you do this, for example, if you take the same functional, you get something depending on the curvature of the sectional curvature of the space. So you cannot say that HR equal to a constant is a critical point. So it's, I mean, we don't know. Then what you can anyway do is to compute the linearized operator of the curvature, the HR+1. And you get this operator, TR, where it's defined as usual when you deal with the HR. This is also in space forms, of course. You get these classical Newton transformation that are defined inductively as P0 equal to the identity, and then PR equal to this combination, where IA is the shape operator. And then here you have the curvature of the space, of course. You have this stuff. Notice that here you have the gradient of F. In general, when you have a space form, this go away. But here you have the gradient of F, and this is what we don't like too much. So we gave a notion of stability using this operator that one calls usually the stability operator, and you can say that M is R stable if there exists a positive constant, a positive function such that TR of U is less than or equal than 0. This is not a very, how to say, you don't need really a large imagination to do this, but in fact, this was already used, and we learned it in this paper by Bueno Galvez Mira, and then we learned that it was used also for This is our MOTS, Anderson, Eichmann, and Metzger. I mean, one can define, it's not so new to define the stability like that. And TR has some problem because it's not self-adjoint. But in fact, what one can do is to define a symmetrized R stability operator starting from TR. I will not write it explicitly, but what you have is that if M is R stable, as we defined here, then you have a sign for this integral, and that's a nice fact. Okay, so let me just finish by telling you some results and plan. Not a lot of results. Results are still, it's a work in progress. So the first, this is not a result. This is just a fact that in spite of not being self-adjoint, one can define the principal eigenvalue of TR. This is standard. And what one can prove with this in this way is that there is no compact R-stable hypersurface in H and cross R. This is not difficult because you find Jacobi function by taking a Killing vector field times n. So it has a sign. I mean, it's not difficult. And then it's interesting to understand what happens for weakly stable. I mean, it's usually it's the same for stable hypersurfaces in Rn. So we define M to be weakly stable if this symmetrized operator has a sign for functions with zero mean on M, as usual, weak stability. And then the question is, for example, are compact rotational hypersurfaces with HR equal to a constant in these two spaces that are very symmetric weakly stable? Why this question? Because in fact, if you look at the constant mean curvature in H2 cross R and S2 cross R, Rabat, Swam proved that in H2 cross R, they are weakly stable, and in S2 cross R, they are weakly stable if H is large enough. Okay, so it's a very interesting question. We think, I mean, we are trying to prove it, let me say like that. Using more or less the same method by Rabat, that of course need some improvement because of the dimension, because of the different kind of equation. Oh, but it's a very interesting question. Another interesting question is the following: under which condition on the constant complete or stable hypersurfaces do not exist or exist? I mean, why this question? Because for the case of mean curvature, this was proved by Chang and by myself, Herbert and Rosenberg. If, for example, in R4 and in R5, there are no constant, complete, stable H surfaces with H positive. So, and there is also a dimension problem there. So what happens for HR? It's an interesting question to deal with, but we are not able to answer for them. We think to have some method, but you know, this is really, we don't know. We don't know. So, but we believe that it's true. That is, some result like that is true. If R is large enough with respect to the curvature of the ambient, then they don't exist. So I finish, and I thank you very much, and I would like to come back there.
Thank you very much, Barbara. Thank you for the talk. And if there is a question or comment, you can turn on the microphone or raise your hand first if you prefer. No No questions?
Comments on the maps are also welcome if you want.
Okay, I have a question, Barbara.
Thank you, Isabel.
You're welcome. So you talk about several generalizations of classical global results, such as Alexandrov theorem and Bernstein theorem, and so on. So there is any generalization in this set for the theorems regarding the size of the Gauss map. So for example, well, for minimal surfaces, you know that the Gauss map cannot omit more than 4 points, but this is probably too much because you have all the complex analysis and so on. But for CMC surfaces, you have the Hoffman, Schoen, Osserman theorem, I think it is, that says that if a constant mean curve, if the Gauss map of a constant mean curvature surface omits an open hemisphere, then it has to be a plane or a cylinder, a trivial example. So are there any results in this line for the higher order mean curvatures?
It is a very interesting question, not to my knowledge. The Gauss map is not studied in general. There are very few results. So it's not something that is studied. Of course, it can be hard because I don't remember, but I think that the results about Gauss map comes also from the Weierstrass type representation.
Yeah, in the case of minimal surfaces, yes, but in the case of constant mean curvature, more partial differential equation, the underlying partial differential equation.
Yeah, I mean, it can be, but it's a good question. I mean, to my knowledge, that there are no results about that. Mm-hmm. So it can be interesting to look at it.
Okay.
Thank you.
Another question?
Hola, Barbara.
Yes.
Hi. Well, first, hi to everyone which is here. My question is about the value of HR. When you think in the case of mean curvature, you are related to the hyperbolic situation. Then you have the difference is H is bigger than 1 or smaller than 1. The situation. I say when you consider the case you are working on, is there some critical value for the case of H, and in particular the H equals 0, HR equals 0 is involved in your result, is excluded?
Okay. Yes, of course, there is as for a hyperbolic space or the product, there is a critical value. But I mean, there is a critical value exactly as for H. Okay, and this for example, in the hyperbolic space is 1, is the same, no? Because it's given by the totally umbilical hypersurfaces. Okay, but for example, you have to look at which result you are looking at. For example, the Bernstein type theorem holds like for mean curvature for any curvature, H positive.
Yeah.
Okay, so if you have the theorem by Docarmo-Lawson and even our theorem is like that. Yeah. If you have a surface that have 1 point at infinity, then the curvature is 1 because it is an orosphere. Yeah. Okay. So this you don't need to take assumption. Then, for example, our last results are for HR equal to 0. But for example, when you look when you look at and you want to classify, for example, rotational surfaces, the behavior is different if you have HR larger than the critical point, the critical value. I don't know the value because it's involved with the n binomial of n over n minus r. So it's a value. So you have, for example, as usual, that compact hypersurface you only have for HR larger or equal to larger than this critical value, and so on. So it is exactly the same.
Okay, thanks. Okay, thanks. Just to add that I hope that in some time, in 1 year, we can meet again, each other, well, in particular you and the other people in here.
Yes, Antonio, I agree with you. I'm looking forward this possibility, really.
Right.
Thank you very much. Thank you to be here.
Yeah.
Okay, thank you, Antonio. Any other questions? Okay, so if not, I would like to thank Barbara for the talk. And thank you all for being here in the seminar. The next week, our speaker will be, I'm going to put, will be Laurent Masset. And it's the same link for the talk. So next Tuesday at the same hour. And in case you are not receiving the information about the seminar by email and you want to receive, then I'm putting in the chat the link so that you can enter your email in this link and you will receive the emails we are sending every Monday for announcing the talk. So I hope to see you all next week, and that's all. Thank you very much for attending.
Bye-bye. Bye-bye.